Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today is the last lecture in this series. In this lecture, we will be looking at whatever we have done till now, and we will also try to look at whatever we couldn't do in this series of lectures. So, we start with, we looked at an algorithm. This is the same question that we asked in the beginning of the lecture series. What is an algorithm? An algorithm is a specific set of step by step instruction for carrying out a procedure or solving a problem. We have seen many examples of algorithms in the last few lectures. So, we have obtained algorithms for given two positive integers, finding the GCD or HCF of the two integers, given a list of items, checking whether a particular object is there in the list or not, given a list of numbers, sort them in an ascending order, given say two sequences of symbols, finding the longest common subsequence, and so on. These are some of the examples that we have seen in this algorithms lecture series. In all of these cases, we have obtained an algorithm. Most of the time, they are not the most natural algorithm. We have also looked at graphs as a mathematical object. Now, what are graphs? They are very simple and very general mathematical objects that help us represent relationships between objects. So, if you remember, we had vertices and edges. The edges were connecting vertices if these two vertices were related. Under this simple notion or definition, we define this graph, and we also saw that many real life problems can be translated into graph problems. Thus, studying graph problems, we argued, is a very important part of algorithms. We looked at some particular problems in this case of graphs. So, we looked at connectivity of graph. Given a graph, is the graph connected? We also asked, given a graph, whether the graph has a cycle, a directed cycle or undirected cycle, whether the graph has an odd cycle or an even cycle. Such kind of questions were asked, and we got algorithms for them. We also looked at, given a graph and possibly weights on the edges, what is the shortest distance between a pair of vertices, or how can we compute the shortest distance from any pair of vertices. So, we looked at the single source shortest path problem and also the all pair shortest path problem. We also looked at the minimum spanning tree, how to obtain a minimum spanning tree of a graph. So, these are some of the problems in graph algorithms that we had encountered. In all these problems that we have seen till now, we had two important tasks. The first one was design an algorithm to solve the problem, and second was analyze the algorithm. We tried to spend equal amount of time to both of these parts, but it is kind of inevitable that people tend to spend more time in the design than the analysis, because once we have the design, sometimes the analysis is either easy to see or sometimes they are very hard to see also. So, when we come to this design of algorithms, we had looked at various techniques that can be used to design an algorithm. We had algorithms like the brute force method, which is basically just do whatever most stupid way of doing things, or we can have some recursive algorithm where a function calls itself again and again, or we also had some more sophisticated techniques of divide and conquer algorithm, of greedy algorithm, of dynamic programming algorithm, and so on. We also saw algorithms that doesn't fit into any of this framework. The most important thing to note about algorithms is that the whole purpose or whole goal of algorithms is to obtain a better algorithm. These techniques are just guidelines to obtain those algorithms. So, in other words, the subject has nothing to do with nothing but solving problems efficiently. And this is where we come. How can we get a better algorithm, better design for algorithm for a particular problem? So, this is a constant effort that keeps on happening. Either newer and newer techniques, newer and newer algorithms are invented, or better and better data structure is invented. Now, data structure is something we have not looked at much in this particular series of lectures, but it is another very important part of algorithms, and they are like assistants to the algorithm. These are the data structures help or provide support to creating better algorithms. We have seen some of it like arrays, like lists and so on, heaps and such kind of stuff, but then the data structures can be much more varied and much more complicated. Depending on the need of the algorithm and need of the problem, a more complicated algorithm is required. So, this subject is basically given look at a problem which has importance in our lives, in a problem that we have to solve in the computers and so on and so forth, and try to come up with better and better algorithms. Now, what do we mean by better algorithm? And this is where we have come to the point of analysis of an algorithm. So, given an algorithm, there are few things that we need to prove. The first thing, of course, the fact that the algorithm works. And what do I mean by the algorithm works? Means given a valid input, the algorithm first of all must stop at some point of time. In other words, the algorithm must terminate. It should output the correct value. These are the two important factors determining the correctness of the algorithm. The algorithm stops and outputs the correct value. This is almost a necessary condition of when I say that an algorithm for a problem. An algorithm has to be correct. But when we try to compare algorithms, we have to understand which algorithm is better than other, and in that case we have to understand how good is the algorithm. As we had done in the last many lectures, the goodness of the algorithm is usually measured by the amount of resources used by the algorithm. So, in this whole set of lectures, we have looked at only these two particular cases. One of them is time, the other one of them is space. So, time basically says that the number of steps made by the algorithm, and the spaces meaning the amount of space required by the algorithm. So, a very important fact I emphasize again, that in the subject of design and analysis of algorithms, we do not measure how good an algorithm is by writing a code and running it on a computer. We do not say that this computer algorithm is better because in this particular form of a Windows computer using this program, the algorithm will output the answer in 5 seconds. No, our whole analysis of the algorithm is very mathematical. It just looks at the number of steps made by the algorithm. You can clearly understand that the number of steps made by the algorithm is independent of how fast each step is computed by the computer. The idea is the computers might become faster and faster day by day, Nowadays possibly they can solve 1000 steps in 1 second, maybe 10 years later they can solve a million steps in 1 second, but still the number of steps required by an algorithm will remain identically same. So, these are a very universal way of computing or analyzing the algorithm. So, we look at the number of steps, and similar techniques are also used for the amount of space required. When we talk about either the space or time, we usually compare, say in this case we look at the time, the maximum number of steps the algorithm requires for any given input. This is what we call the worst case runtime, and this is where we have looked at in most of the lectures. So, again it is not like we say that this algorithm is better because in the input that I gave it has performed good. No, we have to mathematically prove that that algorithm for any input will perform at least this much. So, we have to look at the worst case runtime. There is also a similar one for what is known as the average case runtime, which also we have seen in the case of quicksort algorithm. If you remember that it is the number of steps required on an average number of steps required for computing the input. So, both of them are mathematically very sound definitions. It has nothing to do with implementation of the program or the computer in which it is running or any such thing. To prove them you have to solve it mathematically. We have seen all of it in the last many lectures. Now, how do we compare two inputs, two algorithms? The first thing to understand is that to compare it we have to have a base case. Now, to understand the base case, the idea is always it is measured in terms of the size of the input. So, the space complexity and time complexity are measured in terms of with respect to the size of the input. So, the input is provided to the algorithm. The input can be anything from a number to a or a graph or a sequence of numbers or a word or anything. Now, if a number is given and I say that okay, the number that I am given to you is giving you is 1 million. Now, this 1 million might be a huge number, but to represent that 1 million I will just need log 1 million to the base 2 number of bits, because I can write it in binary and I will provide it to you in that way. And if so, then the input size now becomes log of 1 million and not 1 million. So, we have talked about this input size quite a lot, and we have looked at how space and time complexity are related to the input size. So, this is what we have done mostly in our last few lectures. Let us take a small break now and let us try to understand what all things we have not seen in the last few lectures. Welcome back after the break. So, before the break we looked at what all things we have done. Mainly we have looked at various problems and solved it using different algorithms and analyzed the algorithms. One important thing that we have not done or not done that much is the lower bound. Saying something like prove that a particular algorithm is optimal. What do I mean by that? If you recall that we have proved that merge sort sorts a list of numbers in order n log n steps. Now, can there be a better algorithm? Maybe yes, maybe no, and the answer is no, because we can prove in a different mathematical way that no other algorithm can solve it in better than n log n steps. So, this is what we call as a lower bound. It is another very important part of algorithms to understand how far we have progressed towards our optimal algorithm. If we do not know where to stop, we will never be able to understand when to stop. So, this is a part that we have not done much in our lecture series. So, in general we have the upper bound which is for designing an algorithm. So, upper bound of a particular problem is design an algorithm, and the lower bound is much harder. requires to prove a lower bound using mathematical reduction. So, now let us come to problems. We also tend to look at problems as objects we want to compare. For example, is the problem of sorting easier than the problem of say finding the longest common subsequence? Now, clearly these two problems are so far off in terms of the problem itself that what do I mean by comparing them? So, in other words, we want to classify in some sense a set of problems of equal hardness as a one group, of another hardness of another group. So, you want to classify the problems based on their hardness parameter. So, we also had looked at the asymptotic notations, and where we use the big O notation. In some sense we use the big O notation some sense to hide the constant factors. So, in that it is kind of a neat way of description, and we have already seen things like log n, order n log n, and we know that if an algorithm can be solved in order n steps, then that is better than solving it in order n log n steps, and order n log n steps is better than order n squared steps, and so on. So, this gives us some idea of the algorithm, but what to do with the problem? We are talking about the classification of the problems, not the algorithm. So, for a complexity of a problem, say in the case of sorting, something we have understood very well, we say that the sorting has complexity order n log n because we have a algorithm for sorting which has time n log n, and we have seen that no algorithm for sorting can take less than n log n steps. So, a matching lower bound. So, once we have that, we kind of understand the problem sorting. Now, we are not talking about merge sort or quick sort or any particular sort, but the problem sorting itself has a optimal complexity, and that is in this case order n log n. Once we have the complexity of the problem, we can of course tend to put the problems based on their complexity. We can classify the problems based on their complexity. Now, to obtain, coming back, what is the connection to algorithms is that to understand the complexity of a problem, we have to design algorithms. We also have to do the other part which we have not done, is proving the lower bound, but which is also a big part of the algorithms course. And we would like to classify these problems based on the complexity of the problems. So, here are said two big sacks of problem in some sense. So, we say that a problem has time and space complexity polynomial if the complexity of the problem is a polynomial, means something of the form order n log n, order n square, order n to the power 100, all of this falls in this category. The idea is that we want to distinguish something that can be solved in order n to the power 100 from something that can be solved in order 2 to the power n. The reason is that although n to the power 100 is large compared to 2 to the power n for small n, but as n goes to infinity, 2 to the power n is enormously big compared to n to the power 100. So, we would like to have n to the power 100 rather than 2 to the power n, and under this thing we also have this so called the exponential complexity, which basically says that the complexity is exponential, is like 2 to the power n, or at least not polynomial. So, we have this polynomials and exponentials. Actually, there are much more than that. I am just making this into two small categories. Now, these polynomials are the set of problems for which the complexity is polynomial, and these are what we call tractable problems, problems that we believe can be solved easily. So, the class of problems for which has complexity polynomial in the input size is called P, script P, the special curvy letter P. So, this are the set of what we say easy problems, because a computer can solve it quickly. Now, almost all the problems that we have seen in this lecture series is in P. There are many problems that we know are cannot be in P. For example, if I give you a program and I ask you to check whether the program will ever stop, this particular question As simple as this, as it may sound, this problem is not in P. You cannot solve it in polynomial time, because I can write a program that will not stop for ages and you have no idea when it will stop. And there are problems so for which we don't have a polynomial time algorithm, so we don't know that it is in P, but we also don't know that they are not in P. Then this is the class of problems which is the most interesting, because this is where the ambiguity lies. This is where we don't know the final answer, with is it in P or not in P. Let us try to understand. Look at one such problem. So, recall this coloring of the graph. So, a graph, if you remember, is a set of vertices and set of edges. Edges are lines or connections between vertices, and the goal is to color it in within 3 colors. I ask you, can I color the graph using 3 colors such that you color the vertices with red, blue and green, under the condition that if I have a edge between u and v, then color of u and color of v cannot be same. This is the same problem that we had discussed earlier about coloring the map. I give you the map of India and the goal is to color every state with a different color, so that no 2 adjacent states have the same color. Question is that given a graph, can it be colored with 3 colors? This graph, we don't know of any polynomial time algorithm for solving this problem, but this problem has a nice interesting characterization. It has the property that if I give you a coloring and I ask you, is this a valid coloring? So, I colored the map and ask you, is this a valid map? Then I can check whether it is a valid map in polynomial time, because I all need to look at is all the adjacent states and see whether they are different color or not. That would take me just polynomial time. So, we can, given a coloring, we can check whether the answer is right. So, there are problems for which we do not have a good answer to find, but we can efficiently check if the answer is right. It is like I am a teacher, there is a problem, I do not know how to solve the problem, but as a student you give me an answer and I can verify whether the answer is right. So, it is like a teacher student relationship, and this comes us to the next class called NP. So, NP is the class of problems for which we can check whether a given solution is correct. So, you can think of P to be the class of problems for which we can find a solution. So, it is something like the class of students and who have to find a solution by themselves, and NP is the class of teachers, because they possibly cannot find the problem by themselves, solution by themselves, but given a solution they can check whether the answer is correct, and these are called, the problem is called NP. NP for non-deterministic polynomial time. And what we know is that the class of problems for which we can find a solution, which is P, is a subset of, is also contained in the class of problems for which we can check a solution. Kind of reasonable, correct? If I can solve a problem, I can also check whether the answer is right. So, the class P is a subset of NP. The biggest problem that we have in this field of computer science is question of, is these two classes same? Is P equal to NP? Why is this problem so big? You might have heard of this problem in some places. So, this problem intuitively can be told that is the teacher as smart as the student? Sometimes in Indian context it is told is the Akbar-Birbal setting. So, P is a set of Birbal. Birbal are very intelligent people who can come up with solutions, and NP is Akbar, who cannot come up with a solution of his own, but if Birbal provides the solution, Akbar can check if the solution is right. Now, and question is that is Akbar and Birbal equally intelligent? If this vague question can be translated into mathematics, this is what comes out. P is equal to NP. Some people believe that P is not equal to NP, some people believe P is equal to NP, and there is lots and lots and lots of work being done on this field. The toppest minds in this whole world is working on this problem. This problem many people believe cannot be solved in the next 200 years. Some people believe that can be solved in the next 20 years. But the important thing is that this problem is so important for us day to day life. If this problem is solved, that if somebody comes up with a statement that P is equal to NP, then possibly all our banking, all our security, all our communication, telephone communication, everything can be hacked like easily. Our system will collapse. There is some lots more other things that can be done if P is equal to NP. But if P is not equal to NP, we are in a slightly better shape. But again, you never know. Somebody has to prove to us that P is not equal to NP. Because unless, but maybe P is equal to NP, somebody might be able to prove P is equal to NP, and that person will now have an advantage of hacking into my system. With this, because of the lack of time and because this subject is beyond the scope of this series of lectures, so we cannot go much further than this about explaining this P and P problem. But this is a problem which is called a problem in complexity. Complexity theory is something related to algorithms. So, algorithms helps us to come up with the upper bound. We have an equal dual problem of lower bound, and when we have the dual problem of the lower bound, the upper bound and lower bound problem, when they come together, we have a characterization of problems in terms of hardness, and thus we get this such beautiful questions. So, let me summarize today's lecture. We looked at algorithms, the design of algorithms and analysis of algorithms. We looked at some types of algorithms, the various types that we have looked at, and at the end we also looked at the complexity theory, how our algorithms connects to complexity theory and in the whole scheme of things. With this, we come to the end of this lecture series. In this lecture series, we have discussed about algorithms, and hopefully it was useful for you guys. Thank you.